Today we're doing section 2-2 of Tech Math 2. And it has to do with triangles. So if I take straight segments of lines and I form them somehow, I can do many things with them. Okay, what would we call that figure other than not connected? 1, 2, 3, 4, 5, 6, 7, 8. 8 sides. We wouldn't call it an octagon because when we think of an octagon, we think of it as being a regular type thing of all equal sides, right? But we would call them a polygon. Polygon. A many-sided object. I'm sure that, let's see, poly, probably from the Latin and gon from the Greek. We'll stick with that. Right. Then I could have three-sided objects. So I could do that. 1, 2, 3. And now I can have a triangle. I can have a four-sided object. That would be a right triangle. T-R-I-A-N-G-L-E. We could have four-sided objects. 1, 2, 3, 4. Is that 4? That doesn't look like 4 to me. Delete. Cut. There we go. That's better. I'll do it again. 1, 2, 3, 4. That's better. And that'd be a quadrilateral for 4. Quadrilateral. So lateral being some type of a side, quadra being some type of 4, being 4. And then I could have 5 and I could have 6. I could have a decagon and have 7. Okay, well that's fine. This section has to do with triangles. So my triangles could be all the same size. And does that look almost like all? Pretty much. If these sides are all the same, so he's the same as that, then I'd have a quadrilateral. No, I wouldn't have it. Equilateral triangle. Equilateral triangle. So it's a triangle because it has 3 sides. The sides are all equal, so it's equilateral. Do we know what the measure of the angles are? Do we know what that angle is? They all have to be the same, right? So it would be 60 degrees in an equilateral triangle. So all the angles would be 60 degrees because if I do the sum of the angles of a triangle, I have to get up to some number. I forget what it is. 180. If I have only 2 sides that are equal, that look about like 2 sides that are equal, almost. Then I'd have an isosceles triangle. And isosceles was a Greek mathematician, so he gets a triangle named after him. Isn't that nice? You guys just lived 2,000 years too early. And then if we have what's the difference between a scalene triangle and an acute triangle? I have no idea. Okay, so we have scalene triangles, and I don't think scalene was the name of anybody. And then we have acute, pretty ones. So there's an acute triangle, an obtuse triangle, and a right triangle. All right, so we have scalene, S-C, and I don't think scalene is a guy's name. That's probably left over from the monasteries in Europe. They came up there. Acute. So acute, all the angles are less than 90. And then I have an obtuse, because one of the angles is bigger than 90. And then I've got a right triangle because I got a right angle on it. Okay, so on page 84, how did we make it up to page 84 already anyway? We must have skipped something. The sum of the angles of a triangle is 180 degrees. So at any time, no matter what the triangle is, if I know two of the angles, I can figure out the third one. So that's what that means. And if my triangle is right, so I got a right triangle. All right, so I got a right triangle. Then I've got Pythagorean, whoever it is. Pythagoras, that's who it is. And the Pythagorean theorem says that a squared plus b squared is equal to c squared. And I don't know why I squared these guys, that's really silly. So A, B, and C are the sides of the triangle. If I square them, then I get the hypotenuse. The hypotenuse squared is the sum of the side squares. Now, if you think about that, Pythagoras was 450 BC or so. Could he even do this math? You know, we didn't have decimal numbers yet. How was he squaring numbers? Well, you know, what was he doing to make that work? Well, as you may or may not recall, the Babylonians, several thousand years before then, came up with a numbering system that had 60 numbers in it that you could multiply and add and subtract. And that's why we have 60 minutes and 60 seconds on our clock, because of the Babylonians. But the Greeks would have known that numbering system and would have used it just like we use the decimal system to do their math, and it would have worked out just fine, except that in our case it would not be a good idea. We would be hard pressed to do that in our head. But they were doing it without a calculator. Now, in all fairness to the Greeks and the Babylonians and the ancient Egyptians, they didn't teach the general population math. So the only people that were taught math were the people that had to know the math. So the scribes that had to keep the books had to be able to do math, but the guy that was out there cutting the corn, he didn't have to do it. Did anybody cut the corn in Babylon? No. Why not? Corn came from the New World, right? So there was no corn in Babylon. Okay. All right. But if there were corn in Babylon, then the guy harvesting the corn in Babylon would not be counting it because he wouldn't know. He wouldn't have been taught how. Okay, so now we have more English to worry about. We have a median, and we have an altitude, and we have an angle bisector. So if I have some random triangle, so there's my random triangle, and we're going to go and make copies of it. If I could find the paste command. Oh, bummer. Oh, no. Okay, there we go. So I got random triangles. If I go and I put in a median. So I find the halfway point on each of those things, and then I draw. All right, so if I find the halfway point, the medium in each of those lines, and I draw lines I'm going to hit in the middle. If I draw in altitudes, things that have right angles to the other side, I find that they're going to meet someplace in that triangle. The altitudes are going to bisect each other. If I find half the angle of these guys, if I draw a line to half the angle, then they're going to meet as well, if I could draw my line right. So my altitudes meet at some point, my medians meet in some point, and my angle bisectors meet at some point. Those points are all different points. And they're not the same point, they're all different points. But they do meet at a point, and that might be a reasonable thing to do. And then next thing we have to worry about is the area of a triangle, and that's going to be 1/2 the base times the height. So I got some triangle. There's my triangle. I got a base. I drop down in altitude. That becomes my height. The area becomes 1/2 my base times my height. So that's what I'm going to do. Now, if I look at this and I throw in construction lines, and I say, well, gee, if I did something like this, then this triangle on this side would be the same as that, similar to that triangle there. It had the same area. And if I drew a line over here like that, and these are right angles, then this triangle on this side is similar to, and is the same as the area on that side. What's the area of my rectangle? Well, base times the height. So having the area 1/2 the base times the height makes sense. That's what I ought to do. That's not a rigorous proof of the idea. It's just something that shows that it is. Now we have Heron's formula. Now Heron, you probably, if you listen to the History Channel every now and then, you have Heron is a guy that about 100 BC or so that made a whole lot of cool things. So if you had a statue of Zeus, you'd want the statue of Zeus to have steam coming out. You'd want it to sing a tune. You'd want it to groan somebody that said yes or no when you walked into him. So your temples were places that were mechanically sophisticated in ancient Greek, and same thing with the Romans. And Heron is a guy that made those devices that made the temples more sophisticated. And anyway, so he has a formula that says, in the event that I know all three sides of the triangle, A, B, and C, I know all three sides of a triangle, I can come up with a thing, and I'm going to call it S. S is going to be 1/2 those sides, A plus B plus C. And then I'm going to say the area of my triangle is going to be the square root of S times S minus A times S minus B times S minus C. And the only time in your entire life you're ever going to use this formula is in section 2.2 of the Tech Math book. Okay, so the homework associated with section 2.2, we're going to use it. Maybe it might be on the chapter test, but if it is, I'm going to have to put it up on the board because you're not going to remember it, right? But it allows us to find the area of a triangle that is just some random triangle that would be more difficult to do. All right, but that's something that's about 100 years before Christ. The Heron came up with that. The other issue is, how do I do a square root without a calculator? So he has this idea that I'm going to do this math, but anybody know how we do square roots in base 10 without a calculator? We do it. Well, yeah, we do it with a slide rule is how we would do it. So if I look at the square root of a, I could rewrite that as a to the 1/2. If I take the log of a to the 1/2, that's the same as 1/2 log a. So if I had a slide rule that was marked off on a log scale, so that'd be 1, that'd be 2, that would be 3, 4, 5, 6, 7, 8. Logged in a log scale, and I had some number, and I took half of that number on that log scale, then I would come up with the answer to the square root. So I would do it with logarithms using a slide rule. Now, none of you have ever used a slide rule, right? Okay, so, but I had to use slide rules up until 79. In 79, I got my first calculator. Before that, all my calculations were by slide rule. It was a normal thing to do. Heron didn't have a slide rule because he didn't have base 10. He didn't have logs based on base 10 because he didn't have base 10. That's not for another 700 years. So how exactly he did this square rooting thing in his head, I'm not sure how he did that. But, obviously, it was probably an extraterrestrial, probably, yeah, in order to come up with the thing. But he had steam-driven engines at a time when Watt didn't make the steam-powered engine for another 1,500 years. Angles can be similar. Way to go, that's a cool one. Similar, S-I-M-I-L-A-R. All right, so if that angle and that angle are similar, then that means that angle A is equal to angle A prime. And angle B is equal to angle B prime. And angle C is equal to angle C prime. So that's what a similar triangle means. When the triangle is similar, then the sides, A, B, C, A prime, that doesn't look like a C, B prime, C prime, are proportional. So that means that A is to B as A prime is to B prime. And I can use those relationships to figure out similar triangles. What are they? Okay. We happy with triangles? Get out my calculator just in case I have to push some numbers. All right, I'm good. My calculator's out. Yeah, no, let's see. We only have 24 problems to do. Oh, yeah, that shouldn't be a problem. So, problem number 1, we want the area of the triangle. So 1/2, 6 times 8, 3 times 6, 24 centimeters squared to the area. 1/2 the base times the height. 12 times 11. 132 centimeters squared. Number 3. Oh, way to go. All right, number 3 will take us several more seconds. Okay, so we'll we're not going to draw the stupid triangle the way he has it drawn, right? We're going to draw it our way. So there's our triangle. And we got a right angle. The hypotenuse is 3 640 meters, and we'll call that side 2250 meters, and that side's B. So the issue is we want the area is going to be 1/2 the base times the height. I know the height, but I don't know the base. Or I could tip it up the other way and I could know the base and I could know the height and not the base. But anyway, either way, I got to calculate B. So B is going to equal square root of the hypotenuse squared minus the other side squared. So I'm just using Pythagorean theorem. C squared is equal to A squared plus B squared. I'm solving for B. So that's what I'm doing. Now, when I square something, it could be plus or minus, right? So when I take that square root, I have to decide that B could be plus or minus. But it's a measurement. What does minus 3 inches mean? Well, it means I cut the board in the wrong spot, right? So I go and I make a rafter and I hand it up to the guy that put it in the roof, and hey, this beam is minus 3 inches. Yeah. So it doesn't have too much meaning. Okay, so anyway, square root of 3640 squared plus minus 2250 squared, close parentheses. And so I get that B is 2861.31088888, which I really don't care about because those aren't significant digits. And now I can go back to 1/2 base times the height. So area is 1/2 2861 times 2250. Now, what I wouldn't do is I wouldn't round this guy off. I just leave it in my calculator and go times 2250 divided by 2 and call my answer 23. Way to go. Obviously we have a learning disability problem going on up here. 3218974 meters squared. And then we'd say, well, you know, we only really have 3 significant digits, so we should round it off to 3. 3221234 zeros meters squared. Put in commas. All right, good enough? Good enough. Number 4 would do the same thing, so we'll skip them. Do we have to? Oh, we have to do number 4. Not skipping number 4, we find that we have to find the height because we don't know it. 295 feet. 182 feet. A. So we're going to find that A is equal to square root of the hypotenuse squared, 295 squared, minus 182 squared. And we're going to find A, square root of 295 squared, minus 182 squared. And I end up with 232 plus some decimal stuff. So area is going to be 1/2 182 times 232. Rounded off 3 significant digits, and oh, way to go. And the units are feet squared. All right. Times 182 divided by 2 equals 3 significant digits. Okay, 21100 feet squared. Okay, now we move on. Now, I don't ever recall using the word perimeter in my previous remarks, right? So somehow perimeter snuck in on me and I didn't look at it. So if I have a triangle and I've got side A, B, and C, then the perimeter is A plus B plus C. So it's the adding of those guys going around it. Okay, so I got a triangle. or either that or I have two triangles. 1, 4.2, 28.6, 16.9, 24.0. All right, and we want to find A, the area. Okay, so the area, 1/2 the base times the height. And we'll put that on our calculator later. And then we also want to find the perimeter. And it's going to be 16.9, 24, 28.6. Okay, so we'll do perimeter first. 16.9 plus 24 plus 28.6 equals. So the perimeter is 69.5 inches squared. Oh, not inches squared, inches. All right, and the area is 1/2 times 28.6 times 14.2, and the area is 203.06. Too many significant digits, inches squared. But we're going to hold on to those significant digits for a little while. We're going to go back to Heron's formula. And Heron's formula said the side is going to be 1/2. S is going to be 1/2 the perimeter, right? So 69.5 divided by 2 is 34.75. And the area is supposed to be equal to the square root of S, 34.75, times 34.75 minus 28.6, 34.75 times 24 minus 24. Minus 24, 34.75 minus 16.9, square root of the whole thing. And when we get done, we better get an answer close to 203, otherwise we're going to take Heron and string him up. Okay, so second function answer times, parentheses, second function answer minus 28.6, close parentheses, times second function answer minus 24, close parentheses. I got to go back and put another close parentheses in. Insert, close parentheses. Otherwise, it's going to tell me syntax error, parentheses, second function answer minus 16.9, close parentheses, equals, and Heron says that this triangle has the area of 202.5 inches squared. All right. So, in all fairness to Heron, he blew it. He's off by a half inch squared. So Heron's formula is in fact an approximation of the area, but if I was only going to go to two significant digits, I'd call this guy 200 and I call the other guy 200. Now they're the same. If I was going to go to three significant digits, I have 203 and I have 202.5. Am I rounding up or not? Yeah, so. But I'm off by a little bit, and that's what I wanted to show you. Okay, we're going to do number 8 next. Number 8. And we got a triangle. Boom, boom, boom. 4, 3, 4, 2, 8, 5, 2, 8, no, 2, 8, 2, 8, 5, 2, 8, 5. All right, 2, 8, 5, 2, 8, 5. Okay, well, if this wasn't section 2 of the book, which it is, what I would do is I would go like this and say 285, 285, drop an altitude down that way and call this 217 on this side, 217 on that side. Use trig. No, I could use Pythagorean theorem to find that other side of the triangle, right? I could do that. In fact, I might do that. Do we know that an isosceles, do we know that if I drop an altitude from the top of an isosceles triangle that I'm going to cut the base in two? Is that something that we would know? If that is something that we'd know, then we could do that. If not, we're stuck with Heron's formula. So Heron's formula says S is 1/2 the perimeter, 85 plus 285 plus 434. Okay, so 0.5 times 285 times 2 plus 434. 505. So this is going to be 502. And the area is going to be square root of 502 2 times 285, 502. 502 minus 285, because there's two of them, times, can I do that? I have to square them. I can't take 2 times. Okay, so this guy's going to be squared because there are 2 of them. Okay, that's better. 502 minus 434. Okay, so now I'm applying Heron's formula. Second function square root. Second function answer times parentheses 502, parentheses, second function answer, minus 285, close parentheses, squared, times, parentheses, 502, minus 434, close parentheses, equals, and I end up with my area being 40,092. Okay. Now, if I would have gone with my gut up here and done that, then I would have said that the height is the square root of 285 squared minus 217 squared, and that's 217 in case anybody was wondering. 217 doesn't look any more than like 217 than it did before. Okay. Square root 285 squared minus 217 squared, close parentheses. So my height is 184, and my area would be 1/2 the base times the height. So it'd be 184 times 1/2 times 434. And I end up with an answer of 40,092, number 8, feet squared. And Heron, what did Heron say? 40,000. Oh, thank you, Heron. You came closer this time. Okay, good enough? That was 8. All right, find this, find that. Let's find a problem that's hard. Oh, 19. 19 looks like a good problem. The only problem with 19 is that the answer's in the back of the book and I miss it. Some student might look and tell me how hosed I am. A tower, but because our major is electronics and electrical towers or transmission towers, we might have to do that sometime. A tower 275 feet tall. Yes, I have my tower. 275 feet. There's the ground. I've got a right angle. Okay. If a guide wire is attached 45 feet from the top, right, so I got 45 feet from the top and anchored in the ground 60 feet from the base, 60 feet from the base. So there's my guide wire. How long is the guide wire? Oh, okay. Well, let's see. C squared is equal to A squared plus B squared, right? And I'm trying to find the hypotenuse, which is the C. So C is going to equal square root of, we can agree on 60 squared, and but this side here is going to be 275 minus 45, also known as 230 squared. Okay, so we'll put it on a calculator. Square root 60 squared plus 230 squared, close parentheses, and the guide wire is 238 feet. All right, good enough? 24, and then we'll call it a day. Oh, yeah, I'm supposed to do 24. 24, call it a day. Triangles ABC, let's see, and lines AB and ED are parallel. Okay, so that just, all it's saying is that I have two similar triangles sitting here. And so where's A? A, B, C, D, E. 4-0 for drawing the picture. 24.6, 20.4, 16.4, 40, and everything is in centimeters. Centimeters, 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 centimeters. All right. I want to know E, DE, and I want to know E, let's see, BC. All right, so that's what I want to do. All right, so I'm gonna go for this guy first. Okay, so what we need to know is we need to have these guys two added together. So that's 1 to carry, 1 to carry. So I got 41.0 centimeters on this side. Is that what I got? 24.6 plus 16.4. 41. Okay, good. So now I can go that 41 is to 40 as 24.6 is to DE. And then I can rearrange that and say DE is, that goes on top, that goes on top, that goes on bottom. 40 times 24.6 divided by 41. So I'm cross multiplying 40 divided by 41 times 24.6, and I get that DE is 24 centimeters. Okay, now that I've done that, I'm supposed to find BC. BC. Okay, so I'm going to do the same thing. I'm going to go 41 is to 40 as what? No, not trying to. 41 is to BC. BC. 41 is to BC as 20. BC as 40 is to 24. Okay, so that's good. So BC, cross multiply again, 40 divided by 24 times 41. Well, that seems an awful small. How could I possibly do that? That guy goes on top. Oh, gee. 2 minutes to get it right. Okay, so that guy goes on top. I got 41 times 24 divided by 40. All right, so that's better. 41 times 24 divided by 40. 24.6? 24.6 centimeters. Is that possible? I guess that's possible. Yeah, why not? 24.6 centimeters BC. Okay, good enough. One last chore, and that is to take attendance, which we don't necessarily have to do with the video.